Okay, good morning everyone. So let me do some more result for self-adjoint operator and compact self-adjoint operators. So the first one is an easy one. If we have any self-adjoint operator, so let T belonging to BH be self-adjoint. Then every eigenvalue of T is real. Also, the eigenvectors corresponding to distinct eigenvalues are orthogonal. So also eigenvectors corresponding to distinct eigenvalues are orthogonal. So we have T is self-adjoint, and suppose lambda is an eigenvalue. So let lambda be an eigenvalue of T. Then there exists V not equal to 0 such that TV equal to lambda V. So now if we look at lambda times norm V square, this is same as lambda V inner product with V, and lambda V is TV, so this is TV inner product with V, and this is equal to V inner product with T star V, but T star V is same as TV, so that is V with TV, and then this is V inner product with lambda V, so that is equal to lambda bar times V inner product V, so it is lambda bar norm V square. So this implies lambda is equal to lambda bar since norm V is non-zero. So this implies that lambda belongs to R. Now suppose we have two distinct eigenvalues. Suppose lambda mu are eigenvalues of T and lambda is not equal to mu, and let V1 V2 be eigenvectors corresponding to lambda and mu respectively. So then T V1 is lambda V1 and T V2 is mu V2. We have to show that V1 and V2 are orthogonal. So we need to look at the inner product of V1 and V2. So if we look at lambda times inner product of V1 V2, this is same as lambda V1 inner product V2, which is TV1 inner product with V2, and this is equal to V1 with TV2, since T star is T, and that is equal to V1 inner product with mu V2, and mu is real, so this is equal to mu times V1 V2. This mu belongs to R. We have already seen that any eigenvalue must be real, so this implies lambda minus mu times V1 V2 is equal to 0, which implies V1 inner product V2 is equal to 0, since so in fact this you can show for normal operators also. It is true that the eigenvectors corresponding to distinct eigenvalues will be orthogonal, but the proof will be slightly different. So this says that eigenvalues of a self-adjoint operator are real. In fact, what is true is that even the spectrum of a self-adjoint operator consists of only real numbers. So this I don't know if I'll prove this or not, but let me write this as a remark. If T belong to BH is a self-adjoint operator, then the spectrum of T is a subset of R. So we will prove this if we have time. But we can prove a special case that if we have a compact self-adjoint operator, then the spectrum is subset of R. So let's prove a special case of this. If T is a compact self-adjoint operator. So let me write this proposition. So let T be a compact self-adjoint operator on a Hilbert space H. Then sigma T is a subset of R. So this we can prove easily by using previous results. So if we have anything in the spectrum, so if we take any lambda, so let lambda belongs to a spectrum of T, we want to show that this is real. So if lambda is equal to 0, then of course it is real. If lambda is equal to 0, then lambda belongs to R. And if lambda is non-zero, then since T is compact, what can we say about this lambda? So any non-zero point in the spectrum of a compact operator has to be an eigenvalue, right? So since T is compact, lambda must be an eigenvalue of T. This we have proved before, that any non-zero point in the spectrum of a compact operator is an eigenvalue, and also that the eigen space is finite dimensional in that case. So it is an eigenvalue of finite geometric multiplicity. So now once we know that this is an eigenvalue of T, then because T is self-adjoint, all the eigenvalues must be real, so it has to be real. Since T is self-adjoint by the previous proposition, this lambda must be R in R. So like I said that compactness is not needed. Any self-adjoint operator has a real spectrum, but that requires some other things. So I may prove that later, but right now we have proved for compact self-adjoint operator, every point in the spectrum is a real number. So, okay, next let me prove that for a Hermitian operator, so let's write this proposition. So let T belonging to BH be a self-adjoint operator. Then norm of this operator T is equal to supremum of mod of Tx inner product x is that norm x is equal to 1. So for a self-adjoint operator, norm of T is equal to this supremum of mod Tx inner product with x. So norm x equal to 1. For self-adjoint operator also what is true is that if you take the inner product of Tx with x, it is always a real number, because Tx inner product x is same as x inner product with Tx, because T is self-adjoint. So that is equal to the complex conjugate of Tx with x. So this is actually a real number. So if we look at the supremum of absolute value of these real numbers Tx inner product x, where x varies over the unit sphere, then that gives us norm of T. So to prove this, in one way inequality is clear, that if norm x is equal to 1, And Tx inner product x, this in mod, we know is less than equal to norm of Tx times norm of x. This is by Cauchy-Schwarz. And this is less than equal to norm t times norm x squared, which is equal to norm t. So therefore, this supremum this is less than equal to norm t. This is true for any bounded linear operator, that this supremum is less than equal to norm t. We want to show that for self-adjoint operator, we have equality. So we have to show the other inequality, that norm t is less than equal to this supremum also. So let us write this supremum equal to m. Let m equal to this supremum. So we want to show that norm t is less than equal to m. We have already shown that m is less than equal to norm t. So if we take any x or any x in H, what can we say about the mod of Tx inner product x? This will be less than equal to m times norm x square. Why? Because if x is equal to 0, this is obvious, and if x is non-zero, then you divide by norm x, and then we get, so this is x equal to 0, then obvious, and if x is non-zero, then t of x by norm x, if I take inner product with x by norm x, this in mod is less than equal to m, because m is supremum of all these things where we have unit vector. So this is less than equal to m, and then this is same as txx mod is less than equal to m times norm x square. Now to show that norm t is less than equal to m, we have to show that uh, norm of tx is less than equal to m for all x with norm 1. So let us take any x belong to H such that norm x is equal to 1. So we will show that norm of Tx is less than equal to m. And then by taking the supremum over all such x, we will get norm t is less than equal to m, which will imply norm t less than equal to m. So we have to look at this norm tx. We want to show this is less than equal to m. So first of all, so let y belonging to h be such that norm y is equal to 1 and norm of tx let me write, and tx is equal to norm tx times y. So is it clear that this can be done? So if norm tx is non-zero, then you simply take y equal to tx by norm tx. And if norm tx is equal to 0, then in that case tx is also 0. So you can take any y, right? So this can be chosen. So y equal to tx by norm tx, norm tx, if tx is non-zero. Because if tx is non-zero, then norm tx will be non-zero. And if tx is equal to 0, then you can choose any y. We can take any y with norm y equal to 1. So tx is equal to norm tx times y. So then what is tx inner product with y? So then tx inner product with y, this is equal to tx is norm tx. Yeah. So tx inner product y is same as norm tx y with y, which is equal to norm tx times norm y square, which is norm tx. So norm tx is same as tx inner product y, and that is also x inner product with ty because t is self-adjoint. So therefore, we have norm tx is equal to tx inner product with y, and this is equal to 1/4 of tx plus y inner product with x plus y minus tx minus y inner product with x minus y. because when you expand this, Tx inner product with x will cancel, and similarly Ty inner product y will cancel, and then you will have Tx inner product y, and then plus Ty inner product with x, but that is same as y inner product with T of x, and this is real. So right, so you can check this that when you expand this, maybe let me try to show this. So if you look at T x plus y, inner product with x plus y, this is equal to Txx plus Ty inner product with y plus Tx inner product with y and Ty inner product with x. So this is Txx, Tyy, and Tx inner product with y is equal to norm of Tx. And what is Ty inner product with x? That is y inner product with the Tx, but that is also equal to this. So let me write here it also. Ty inner product with x, this will be equal to y inner product with T of x, and this again if you write y inner product with norm Tx times y, and then norm Tx comes out, this is also norm Tx. So Ty inner product with x is also equal to norm Tx. So this is also norm Tx. So you get 2 times norm Tx here, and similarly this Tx minus y with x minus y, this will be Txx plus Tyy, and then we get minus Tx with y and minus Ty with x. So that is again equal to Txx plus Tyy minus norm Tx, and this is also norm Tx. So if you subtract, then you will get 4 times norm Tx is this. Now we know that this Tx plus y, this is less than equal to m times. So we have shown here that mod of Tx inner product with x is less than equal to m times norm x square, right? So Tx plus y, x plus y, because this is a real and its mod is less than equal to m times norm x square. So this will be less than equal to m times norm of x plus y square, and minus of Tx minus y, x minus y. This is also less than equal to m times norm of x minus y square. This is by the definition of this m as the supremum. So we get this, and then this will imply, so therefore norm Tx is less than equal to 1/4 of m norm x plus y square plus norm x minus y square. And then by parallelogram law, norm x plus y square plus norm x minus y square is 2 times norm x square plus norm y square. So this is equal to m by 4 times 2 norm x square plus 2 norm y square. And this is equal to m, because norm x and norm y are equal to 1. So we showed that norm of Tx is less than equal to m. So hence we are done. Right. So this so primum of this thing, this is sometimes called the numerical radius of operator T, and this inner product of Tx with x, where x varies over the unit sphere, this is called the numerical range of T. So this says that for self-adjoint operator, norm of T is equal to the numerical radius of T. This in general is not true if T is not self-adjoint. So you can try to construct example where the norm T is strictly bigger than this supremum. Okay, so in fact, for a self-adjoint operator, this inner product of Tx with x, this is always a real number. So if we look at the infimum of this inner product of Txx, suppose that is small m, and say capital M is the supremum of inner product Txx, where x varies over unit sphere, then I mean, one can show that the spectrum of T is between small m and capital M. So it is okay. So now let me prove one result about compact self-adjoint operator. Uh, Theorem. Let T belonging to BH be a compact self-adjoint operator. Then either norm T or minus norm T is an eigenvalue of T. So that means that because we know that eigenvalue of self-adjoint operators are real, so this says that there exists an eigenvalue lambda of t whose absolute value is norm t. So let us prove this result. Okay, so we will use the previous proposition. So we know that norm t is equal to supremum of this thing. So right, so first of all, if t is equal to 0, then it is obviously true. Right, because for t equal to 0, if we have 0 operator, then 0 is always an eigenvalue. So in that case, norm t is 0. So this is true. So let's assume that t is non-zero. Now, what we know is that by the previous proposition, norm t is equal to supremum of mod txx with norm x equal to 1. This is because t is self-adjoint. So therefore, we can find a sequence xn. So there exists a sequence xn in H with norm xn equal to 1 and this mod of txn xn, this converges to norm t, right? Because the supremum is equal to norm t, so we can find a sequence here which converges to norm t. Now, because t is compact operator and this norm xn is equal to 1, so txn will have a convergent subsequence. So since t is compact, this txn has a convergent subsequence. So we may assume this Txn converges right. So instead of choosing this sequence xn, if I choose uh, that xnk, then that will also satisfy norm xnk equal to 1. And because we have this sequence converges to norm t, then this, for the subsequence also it will converge to norm t. So I'm not writing the subsequence. Now whatever that subsequence is, we are calling that as the sequence xn. So we are assuming that this sequence itself is convergent, and suppose it is convergent to, so let Txn converges to some let's call Txn converges to some y naught. So then this Txn xn, that norm converges to norm t. Uh, right. In fact, here we may assume again that we can remove this absolute value also. So we have mod of this converges to norm t. So we remove this mod. So because these are real numbers, and if mod of some an converges to some real number a, then there will be a subsequence such that uh, subsequence will converge to a also, right? So I'm removing the mod here. So Txn xn converges to norm t. Now Txn converges to y naught. So right. So now if we look at norm of y naught square, this is y naught inner product with y naught, and txn converges to y naught. So okay, let me write like this. So yeah, so if we look at norm of y naught, this is equal to limit of norm of txn, because txn converges to y naught, so norm txn will converge to norm y naught, and this norm txn, this txn xn, this will be less than equal to norm of txn times norm xn, but norm xn is equal to 1. So this is norm txn. So norm txn is bigger than equal to this, and this converges to norm t. So this will imply that norm y naught, which is limit of norm txn, this will be bigger than equal to limit of txn xn, which is norm t. So we get that the norm of this y naught is bigger than equal to norm t. Norm of y naught is greater than equal to norm of t. What we have to show that this norm t or minus norm t is an eigenvalue of t. So now let us look at txn minus Okay, instead of this, okay, let me go back here. And what we had here is that norm t is equal to supremum of this. Then we said that there exists a sequence xn such that this t, this actually is not correct because this may be negative. So in that case, this can converge to minus norm t also. So what I'll say is that there exists a sequence xn such that xn converges to lambda. This is a real number with mod lambda equal to norm t. So that means that we must have a sequence which converges to either norm t or minus norm t. So xn converges to some lambda where mod lambda is equal to norm t. So then we are assuming that txn is convergent, so it converges to y naught, and then y naught, norm of y naught is bigger than equal to this lambda. So this, instead of norm t, I have this is equal to lambda. So norm y naught is bigger than equal to this lambda. Now we want to show that this lambda is an eigenvalue of t. So now if we look at txn minus lambda xn, this norm square, this is equal to norm of txn square minus 2 times real part of txn with lambda xn and plus is lambda square times norm xn square. So, but xn that is a real number and lambda is also real. So this real part can be removed. So this actually I can just write minus 2 times this, and then this is equal to this will be less than equal to norm t square because norm xn is equal to 1. So this is less than equal to norm t times norm xn. So this is less than equal to norm t square minus 2 lambda exn inner product with xn plus lambda square because norm xn square is equal to 1. So we get this. Now as n tends to infinity, xn, this inner product converges to lambda. So and this lambda square is equal to norm t square. So this will be equal to 2 lambda square minus 2 lambda txn with xn. So because this converges to lambda, this goes to 0 as n goes to infinity. So what does this imply? So this will imply that this lambda I minus t xn, this goes to 0 as n goes to infinity. So now if we look at xn, so xn can be written as, or let's write t minus lambda I. So txn minus lambda xn, that goes to 0. Now xn can be written as, right. So this is equal to 1 by lambda. So this is where we are using that norm t is non-zero. So this lambda is non-zero. So 1 by lambda times txn minus t minus lambda I xn. Right, because txn cancels and then we get lambda xn divided by lambda, so that is xn. So what we know is that t minus lambda I xn, this goes to 0, and txn, that converges to y naught. Right, so this converges to 1 by lambda times y naught minus 0, which is equal to y naught by lambda. So what we have shown is that this xn must converge to y naught by lambda, and if xn converges to y naught by lambda, then txn will converge to ty naught by lambda. So this implies txn converges to ty naught by lambda, but we have seen that txn converges to y naught. So this implies ty naught by lambda is equal to y naught. Txn converges to y naught. So this implies that ty naught is equal to lambda times y naught, which implies lambda is an eigenvalue. Because y naught is non-zero, because this norm y naught is bigger than equal to lambda, which is equal to this norm t, and norm t is bigger than 0. So this y naught is a non-zero vector, and we have shown that ty naught is equal to lambda y naught, which means that lambda is an eigenvalue of t, but the lambda was a real number with mod lambda equal to norm t. So this implies that there exists an eigenvector. So therefore, we have either norm t or minus norm t is an eigenvalue. Is this clear? So in this, both compactness and self-adjoint are needed. So if we have a compact operator and also self-adjoint, then we have that either norm t or minus norm t must be an eigenvalue of t. So time is up, so I'll stop here. So remember that tomorrow we will have our second quiz, and then Thursday we will have another class. So I'll try to at least state the spectral theorem for the compact self-adjoint operator. Maybe prove a little bit, and then if we have any more class, then we can do some more things. So any question? So some of you have emailed me about weightage for the quiz and the major exam. So some of you want that we should have 30% for the quiz instead of 20%. So what I have thought is, because initially I said that the midterm exam will be 30% and 20% for quiz and 50% major. But because many of you are feeling that 50% for major is too much, you want 40% weightage. So instead of changing the weightage for major to be 40%, what I can do is that the quiz I have taken for 10 marks, and 10 more marks will be quiz 2, so that will be 20 marks. And major I'll take for 40 marks, and then whichever you have done better. So out of 20 the quiz marks and 40 will be major. So suppose you have performed better in the quiz, then I'll make the quiz to be 30% weightage. And if you do better in the major exam, then the major will be for 50 and quiz will be 20. So it will be quiz 30, major 40, or quiz 20 and major 50, depending on which one you do better. So that will be beneficial for all the students. So if you perform better in the major exam, then that will be 50%. Otherwise, quiz will be 30 and major will be 50. Major will be E40. So and the syllabus for the major is obviously like everything that we have covered. So it will be the whole syllabus. And some of you were asking whether it will be like you can use the notes or not, because this time it will be offline as well as online. So that I'll decide and let you know by email if you are allowed to use the class notes or not. Okay, so I'll stop here.